My name is Gary Schnell, and I'd like to welcome you into my home near Milwaukee, Wisconsin, where I'm doing a series of YouTube videos in an effort to highlight different areas of my book, recently published, called Consciousness, All in One and One in All. This particular video will cover Chapter 4, All is Relative, because it is about the theory of relativity. And I'm going to give away the most important point at the beginning because I'm going to emphasize it at the end. And that is that neither space nor time are absolutes. And I think it's important to keep that in mind as we're talking about what is and isn't absolute, and where consciousness might fit if space and time aren't absolute. The theory of relativity actually encompasses two different theories. The special theory of relativity has nothing to do with gravity. The general theory of relativity, developed later by Einstein, has to do with space-time and gravity as related to space-time. The first of the two theories, the special theory, is the one that probably most of us are familiar with. It includes the equation E equals mc squared. It sprung out of the work of a couple of people in the later 1800s named Michelson and Morley, who set about to find the medium through which light was propagated. They assumed light to be a physical entity that needed to travel through something. They could not find what light traveled through because it's not the physical entity they thought, and it has nothing through which it needs to propagate. Indeed, light is its own frame of reference. It is the frame of reference. And it is thought that nothing can exceed the speed of light because it is the frame of reference. Now, out of the special theory of relativity, developed the notions that time can dilate and space can contract. The laws of physics don't change, but they are experienced by people relative to their frame of reference. And what that means is that, let's say we have two twins. One decides she wants to go traveling through the stars, and the other decides he wants to stay home with his family. Well, they say goodbye to each other, and the first twin, well, she goes rocketing off into space. Now, as her spaceship leaves, and it's going so fast right away, it appears shorter to the person, to her twin that's left on the ground. Not because it absolutely is shorter; it's the same length, really, but it appears it's the length of it has contracted. Now, the first twin, as she travels off into space, she decides she's going to come home after 2 years. She misses her twin brother, and so she comes home after experiencing 2 years. Now, what she finds is that her brother has long since died. And that has to do with the notion of time dilation. As she traveled closer to the speed of light, time dilated because of her faster travel. And indeed, we notice this in very small scales on Earth when we do different measurements. This is on a much larger scale. So he had long since died. Now, Does that mean that she and he had experienced time differently? No. What it means is that for her, 2 years was 2 years, and for him, 2 years was 2 years as well, except that her time was dilated and his was not. So when she came back, he had died. I think that this is very important because it lets us know that space and time are not absolutes. The general theory of relativity was developed later, and that has to do with gravity. And what Einstein postulated that our universe is not just three-dimensional height, weight, length, but that it also includes time. The best way to explain this is that consider our little solar system, our sun, and the planets around it, all revolving around the sun. Now, if you just look at the idea that, this is essentially a sphere or an ellipse of planets going around a sun, then our little solar system would be cut off from the rest of the universe, just as any other revolving solar system, or even considering our galaxy, the Milky Way, would be cut off from all the other galaxies. So how are we to reconcile this? Well, the best way to reconcile this is by including time as a variable in the space and time, such that when we multiply the spatial dimensions by time, we end up not with an enclosed ellipse, we end up with a flattened helix, such that all is connected. Nothing is cut off from anything else. But what this means is that there's a curvature to space, and such that there's a horizon, just like there is on Earth. At some point the sun goes down, and even though we don't see it anymore, people beyond our horizon, they do see it. Well, it's the same thing with our universe. At some point there's a horizon beyond which we can't appreciate what lies there. And what we're getting into here is the idea of non-locality. Beyond the horizon, we don't know. Up until the horizon, we do know. It's non-local. Now, the other thing that we can appreciate from a non-locality standpoint is that the galaxies that are a great distance from us, the stars, they are redshifted. They are traveling away from us, which is the cause of the redshift. It is lengthening the light that's coming from the star, and by lengthening it, it's making it appear red when we look at it through our telescopes. Now, this would suggest that the universe is traveling faster than the speed of light, because the light is redshifted as it gets farther and farther away from us. But indeed, what's happening is the light, the universe, is being pulled. The whole universe is expanding. The universe isn't traveling faster and faster, so that while it appears that these things are traveling away from us, they're being pulled away from us, faster than the speed of light. And so the light from them appears redshifted, just like if they were to look at us, we would appear redshifted to them. And that, again, is a function of non-locality. Now, at some point, there will be a horizon beyond which we can't see these redshifted stars. We'll see other redshifted stars, and the same thing will happen as they look back at us. The universe is curved, and it is expanding. Now, the other thing to appreciate that the general theory of relativity addresses is the notion of space being bent by gravity, so that Jupiter bends space around it more than Earth bends space. And the sun bends space more than Jupiter or Earth bends space. So that light from distant stars has to, in a way, it can travel around other stars. It's called lensing. And that's because of this phenomenon of bending light. It's kind of like a trampoline. If my granddaughter's on the trampoline and I'm on the trampoline, space will the trampoline will be bent more by me than by my daughter, and that's kind of what's happening with space in space-time. So I hope this illustrates in a way that's understandable the theory of relativity. I appreciate your time. If you have any questions or comments, feel free to add them. I'll do my best to respond to them in as timely a fashion as I can. Thank you very much, and stay well.